Okay, everybody, I want to welcome you to join us for a preview to see CFX ANSYS CFD version 12 and through this webinar. So in here, I'll be presenting a simple case from start to finish to see the components of a CFD analysis in ANSYS CFD 12. Okay, so let's get started. First of all, I have a couple slides to show what ANSYS Workbench environment, all the pieces, integrating into the environment, Workbench environment, and for a CFD analysis. In this diagram that you can see, with any CFD analysis, we need to have a geometry. And in ANSYS, we use Design Modeler to handle the geometry. Either we import a geometry from a CAD system, or you can generate your geometry in Design Modeler. Once the geometry is set, and you bring the geometry to meshing module in so-called ANSYS meshing platform. And that will be served as the meshing tool for both CFX and Fluent, the two solvers in version 12 release. And once the solution is completed, it's converged, and we will take the results to post-processing. Any version 12 release is being named CFD Post. So a unique single post-processing tool will be available for both CFX and Fluent for the ANSYS CFD analysis. So that's the flow chart in ANSYS CFD 12 release, and from start to finish to complete CFD analysis. So next slide, and just outline these components with Design Modeler, and to meshing, and to solvers. When we come to a solver part, you have the choice of either go with the CFX route, or you go with the Fluent route in 12. And once it's converged, of course, you take that into post-processing. So today, we'll be looking at a simple geometry. It's like a pitot tube, right? And you measure the airspeed and pressure variation in here. So that's the geometry. I have a probe, and we take advantage of the symmetry of the probe, and we solve half of the domain and use a symmetry plane in the middle of the probe, and so slice this probe in half. So this probe is being suspended in the middle of the air, and air will go through the probe, go around the probe, and it will also go into the probe. And so there's an internal flow passage sitting in the probe, and air will go through. And that's the external geometry, external surfaces of the probe, and where air is going to go around it. So that's the view from a symmetry plane. Okay. So the flow setup for this question is rather simple. We're using air, isothermal, so there's no temperature, no heating, no heat transfer involved in this calculation. Fully turbulent flow. We're doing a steady state analysis, and assuming I have incoming flow at 30 meters per second, and we calculate the pressure drop, going through the pressure going through the probe from inlet to exit, and based on the geometry and the flow configuration. So at the end, I will also demonstrate in 12 if you want to create a simple geometry variable and to iterate on geometry variations, and you could have done it very easily in 12 by just changing one geometry parameter, and you check updates on the project page, and that will update your solution from the beginning to the end. And you'll see this case, I'll demo this case in the next 25 to 30 minutes. You get to see every piece of the software in action. Okay, so let's minimize that. What you see here on the screen is ANSYS 12 Workbench project page. And these are the analysis system, and you can select what kind of analysis that you want to carry out. Is CFX analysis or Fluent analysis, or the rest of the section here related to FEA for steady state structure, thermal analysis, and so forth, right? So today, we're going to be looking at doing a flow analysis, for example, using CFX. and you can relate use the same analogy to do a fluid analysis. It's the same steps, except the solver is being replaced by Fluent. So in 12, the project page, I'm just going to use a drag and drop system and come to project schematic page, all the cells here. Tell ANSYS I'm going to do a fluid analysis, right? And I'm going to use CFX solver. So immediately you will see like a project workflow box is being created. And it tells you in order to complete a CFX or flow analysis, CFD analysis, you need to have all these components that we just talked about: geometry, mesh, and you need to set up the solution in CFX Pre. You run it and look at the results, okay? So first piece, of course, we want to bring in the geometry. Right-click, I would create or import the pitot tube geometry. What it looks like, I will open up the design modeler software we just mentioned earlier in the PowerPoint page. And design modeler will be the tool to handle geometry import function as interfacing with the major CAD programs, or you can create this geometry in here easily using its geometric generation tools. So this is our pitot tube, and that's the symmetry plane, and that's the two solid surfaces, and that's the internal flow passage within the tube, and that's the external flow domain. So in here, we have two parts. The solid part represents the solid geometry of the tube, which we're not going to be solving in this case. And the flow domain representing the flow domain, which is the external flow field of the pitot tube and the internal flow passage of the tube. Okay. So that's our geometry, right? Assuming we're okay on that, and we have our geometry set up. The next component will be meshing. So let's take the geometry into the so-called AMP, ANSYS Meshing Platform. Okay. The geometry will be brawling automatically, and it will show up in just a couple of seconds. Both the solid and the flow geometry are present in here, right? And if you notice on your right, there's a panel about meshing options, right? The default meshing method will come in as automatic, and which means the mesher is going to pick what's the best option or what's the most appropriate. What's the to create a default mesh. Of course, and you have all the other options available. You can create tetrahedrons, you can create a swept mesh, and you can go into CFX mesh to do a more detailed meshing. So in this case, we'll stay with the default method. Right? Before we start, we want to suppress the solid geometry because we're not doing any solid analysis. We're interested to resolve the flow domain, which there are two pieces: the external flow field and this internal pipe, internal tube section of the probe, right? As you can see here, I have not done anything without specifying any sizing function or allocation by just using the meshing platform default, which will provide its best, a meshing approach on the topology, on the edge size, and on the proximity, and so forth. Create a default mesh. I'm going to do it right here. Right-click on mesh, just select Generate Mesh. In a matter of seconds, and we have a mesh. You see there are two pieces of mesh being created: the external flow field and the internal flow field. They both are meshed. So literally, the mesh was generated in front of our eyes in about 5 seconds. So that completes the meshing section. Both our internal flow domain and external are meshed accordingly. So we press Update and save the mesh data and closing the meshing module. And up to this point, we're going to complete each one of these cells, right? Each one of these elements for this analysis. When you see a check mark that means that section is done. So we're ready to move on to the setup section, which we're going to define the flow, physics, inlet, outlet, boundary conditions, and the numerical parameters, so forth, for this calculation. So because Workbench provides a fully integrated environment, so once the meshing is completed, you don't have to go through the import meshing step and situation like that, and it will be directly brought into CFX Pre, which is this physics setup page. We're going to define the analysis for this probe calculation. As outlined in the PowerPoint file, and we're going to set up airflow for 30 meters per second going through this probe, and we're going to see pressure drop, velocity contours, and pressure variations across the probe, and average pressure on the probe surface, and so forth. Right? So first of all, we want to define what we're solving. And in the setup, it creates an automatic default domain. If we look at what's there, the working fluid is air, and we're using isothermal. We're not calculating heat transfer or in the compressible flow regime, so we can stay with isothermal. With turbulence model included, that default model will be Capsilon. And if you prefer, there is quite a selection of different turbulence models available, from the standard to equation, Capsilon, K omega, and to very more elaborate, highly closure models to RNG and to large eddy simulation and so forth. So default is Capsilon. We're going to stay with that for our probe calculation. So we finished selecting the physics, or what equation we're going to solve for this domain, which means we're solving the maybe the Stokes equation and with continuity equation and then and epsilon equation for this calculation. So next up, we'll generate the boundary conditions. Insert inflow, boundary condition name. I'm going to assign that service called in. I'm going to pick from screen. This is a feature available in CFX Pre. I can select the surface from screen and assign boundary condition detail. I'll enter 30 meters per second. That will be my inflow velocity. Right? Next off, I rotate the model. I will insert the exit boundary condition. I'm going to assign that surface to be out. And this time, the boundary type is an outlet. In similar way, I'm going to select that surface and provide a boundary condition for that surface. What the number I just entered is gauge pressure relative to ambient pressure. If I enter 0 Pascal, which means the flow is exiting at 1 atm, that would be the ambient pressure situation. So next off, I'm going to create the symmetry condition. Right? And I'm going to call that boundary condition sim, representing symmetry. This time, I'm going to select the boundary condition type to be symmetry. And I will select this surface. That's the symmetry surface for the external flow field. And that surface, that will be the symmetry plane for the internal flow domain inside the probe, and the two of them. And that represents the symmetry boundary condition right there. Okay. So what's left? And we have this cylindrical surface representing like the far field of the domain. I can simply insert a boundary called that cylinder, for example, and treat it as a wall. And I'll pick that surface, the cylindrical surface, and create that boundary condition. And what's left will be the probe surfaces. Those are the external and the internal surfaces of the probe. I can simply rename that and assign a boundary group called probe, representing the probe surfaces. So at this point, I finished a setup of the boundary conditions that are required in this domain. I have inflow, I have outflow, I have symmetry, and the probe surfaces will be assigned to wall boundary conditions. So next step, we'll be generating numerical parameters And I will use the default scheme provided by CFX. In this case, it's high-resolution scheme. It provides second-order accurate solutions everywhere throughout the flow field. And I'm going to assign 100 iterations, or when residual reaches 10 to the minus 4, which is small, representing roughly about 0.1% oscillation of the flow value, which can be taken as a steady-state approach as being achieved. So right now, I have completed the setup for the simple calculation. And I can just say exit the setup page and go to the next step, which is solution, and bring that up. That will give me the solution manager, and I can start the solution and calculation right there and monitor the solution in progress. That's the solution setup page. I can simply press start run, and you will see the screen starts to update, and on the right, it's a text output window. That's when the solver takes in the information of this case. And, to interpolate the mesh nodes, elements, boundary conditions, assignment, and start calculation. And you see the solution in progress, going through iterations 1, 2, it's converged. On the graphics window, representing the residual, when we assign to 10 to the minus 4, and that will be taken as steady-state steady-state solutions being converged. As we can see now, it takes a matter of 25 seconds, less than 30 seconds, to converge this analysis to steady state, which means all residuals has been reduced to lower than 10 to the minus 4 level. And we'll treat that as a steady state solution has been established. So in this domain, if I look at the overall element count, roughly is about 30,000 in that range. And I can converge the solution in less than 30 seconds, and provides a very good preview of what is happening in the external and the internal flow field of the probe. So once this is done, I'll exit out of the solution manager. I'm going to look at the results now, right, to see what is happening. I simply right-click and take that into the post processor, and that would be the CFD Post. And it is designed to handle both Fluent and CFX solution outputs. And it has it was established based on the CFX Post in 11.0 release. And now this is capable of post-processing Fluent and CFX results. So the solutions here, and it has all the 3D information that we just calculated in the flow domain. First of all, say for example, let's look at the velocity distribution in the center of the thing on the symmetry plane. So we're going to assign a contour plot. I'm going to plot velocity and look at the distribution. What is it like? And there you go. I have velocity, at infinity, a free stream in 30 meters per second, and going through the internal section of the probe, and these are the external section of the probe. And I can also generate more. For example, I want to see flow directions. I can create a velocity vector, assign that to the same location, and to see how the flow goes. And these are the flow solutions, and it captures some of the recirculation region in the back of the pitot tube. Okay. And you can create a sequence of post-processing and to look at solutions right here. Okay. I can plot another contour. For example, I want to see the surface pressure on the probe surface, right? And this is the surface pressure, and apparently you see when the flow entering the internal flow section and it hits this wall, it somehow has close to a stagnation point, so I see a higher pressure when the flow just first hit the probe surfaces. And then flow will accelerate, which creates a slight pressure drop on the contour cylindrical section, and also on the edge of the bar there. So you can generate all these plots as you wish. And I want to do a little more on here just to interpret a CFD solution will not be limited to just looking at color plots and contour those pretty pictures. I can get useful engineering data out of it as well. For example, I want to look at pressure drop, right? That's a very common parameter in the flow analysis. I can create a very simple expression, and in this analysis, I will call that dP, representing pressure drop. What I'm calculating is I will calculate average pressure at inlet surface minus the pressure at outlet surface. That's a scripting tool provided in CFD Post to make all this calculation very, very easy. I simply write out this script and press apply button. There you go. That's my pressure drop, which means I have roughly 70 pascal pressure drop from inlet to the exit for this calculation. Another convenient tool I want to introduce is I can calculate using a function calculator provided in CFD Post. I can calculate, for example, surface pressure. Select area average pressure on the probe surfaces, right? So I'm calculating the area average pressure on the entire surface of the probe. And by pressing the calculate button, there you go, that will be my average pressure on the probe surface. By using the same terminology, you can literally create endless numbers, of getting the plots, getting the quantity that you like to see, getting a flow solution that you like to see, and so forth from CFD Post, and use those engineering quantities and to guide your design process. Okay, so that basically completes design analysis. Okay, so probably many of you will ask, what if I want to change a little parameter which controlling a part of the probe geometry? I want to do it again. In ANSYS 12, in ANSYS CFD 12, in the project schematic diagram, in the project schema, we can achieve that rather easily. What I'm going to do is I'm going to make a variation of this design by changing the internal tube size, internal flow passage size of the probe to make it smaller, right? And so I will be editing the geometry. I created a duplicate section of the solution that we just did from the first segment, right? So we do have the geometry file here. So in here, I have a parameter to control the geometry of the internal flow passage. I can simply decrease the parameter from 0.95 millimeter to 0.5 millimeter and press generate. And as you can see, the internal flow section has been reduced to a much smaller pipe, much smaller duct. Okay, and I'm going to analyze this. So if, for example, you're going to go through many of these variations, and in ANSYS CFD 12, this process will become very convenient, and that's all I need to do. And you can sort of interpret the same analogy and to, if you have a CAD model, and design modeler will be served as the same with the service bridge to bring your CAD file in and provides a bi-directional link, between ANSYS tools and the CAD model and the CAD program. So if you have a parameter defined in CAD program, and you can edit the definition there and change the sizing of the tube, for example, in the CAD, in Pro-E or SolidWorks and UG, and press update, and geometry will be reflected in the design right here. So at this point, I have a new geometry, right? So all I need to do right here, as you can see, you might want to go through all these steps to check, but literally all I need to do is just go press update project. So because of the link between all this component, all in one single integrated environment in Workbench project. So if you notice the progress, what it's doing now, so ANSYS is going to go through each one of these individual components to update the setup. You do not have to go in each one of the program and to go through all the steps again. I mean, you notice on screen here, the check mark is being added to the meshing part, which means the mesh is completed for the new geometry to reflect the change of the internal flow space of the probe. And after meshing, the setup page has also been provided with a check mark, which means the setup has been updated using the new mesh. And we're now in the solution part, and the state is showing it's solving. So we're going through the iterations from 1 maybe to 30. And now you notice the solution is completed. Okay? It's completed, and it's ready for post-processing. So in a matter of a minute or two, and the entire analysis is updated with the most recent geometry and mesh information. And this looks like a dark magic, but as a matter of fact, it's not. We can take a look of each one of these individual components just to make sure it's really been updated. So let's take a look at the meshing section. And as you can see, the geometry is being reflected here. We have a much smaller internal tube. And as indeed, it has been meshed as well. And if we exit the mesh section, and let's look at the setup. So that will take us to CFX Pre, and to see, without going through the same procedure, bringing in a mesh and to reassign the boundary conditions and so forth, the setup is there. And the new geometry and the flow field is being updated right there to reflect the much smaller tube space, and much smaller internal flow passage inside the probe. So that is done. Okay. Of course, and we can, solution is now complete. We can look at the solution to see what it's like as well. And all the objects I created the first time, the contour, which represents on the symmetry surface, and the pressure contour on the external surface of the probe, they are all there. Or I can look at velocity vectors as the flow go into the tube and it go around the probe section, right? So they are there. I'm going to do something a little bit more. So now we have two designs. I want to compare the differences between these two designs, right? And which one is better. I'm going to put these two solutions side by side so it will be easier to compare the differences and from design A to design B. So to do that, simply in the Workbench project page, I'm going to grab using the drag and drop scheme. Take the solution from A block, that would be the first analysis, and put and drop it to the result section in B block, right? So you will see a link is being established in Workbench saying this solution will be provided for viewing and comparison purposes in here. So if we go back to CFD Post again, it will load two solutions automatically, and I can arrange the view panel. And I do have two solutions right here, and the top and the bottom, and I can synchronize them. So they would always show me when I rotate the model, and they will show me the same section and of on both models I'm looking at. And you notice the first one on top is the second design with a smaller internal flow passage of the probe. And the bottom one is the first design with much larger internal flow passage. And with that, we can look at contour, and that would be displayed on both models. So by doing that, you can easily compare the flow solution differences between the first design and the second design, and focus in the region of interest to pick out the best solution and between these designs. And you can do 3 or you can do 4 and in sequence and compare and bring the solutions in CFD Post and compare the differences. So that shows you the graphics, the velocity contour, and the pressure contour on the probe surfaces. Okay, and if we look at what we generated for calculation, right? We generate the pressure drop. Same thing here. We want to evaluate first solution. That will give us the design A. That's the pressure drop and from the first solution. Or we look at the second solution. I can evaluate the pressure drop for the second solution. I mean, I have the same calculation tool. I can calculate the pressure differences on the average surface pressure, so forth, on many situations. On the first case, calculate the average pressure for first case, and so forth. You can do all the same quantitative analysis from the based on the CFD solution, first solution and the second solution, and so forth. So in 12, based on the architecture and program schema, it is very convenient to create a sequence of design iteration. Or you have, based on this situation, I mean, you can easily perform a sequence of design level CFD analysis. Once your baseline case is established, if I exit out Post for a second, go back to project page. Once your baseline analysis is established, and you can go through geometry variations as well as flow variations, and to address the design and the performance of each one of the conditions. Okay, so at this point, I would like to conclude today's webinar, and thank you for your participation. And we'll now come to question section. If you have any questions, please feel free to ask. Thank you.